Hello, this is Mrs. Johnson. This is MAT221, Calculus 1. This is section 5.2, which talks about the definite integral as area. Now, we were just talking about this particular curve down here. And remember, no matter what function we see that sits next to integration symbol, this function that we're talking about, whatever function it happens to be, no matter what the notation, it will always be a derivative function of some other function that we call the antiderivative. So if this is the f of t curve, this blue curve that you see below is the f of t curve, it is the derivative of another curve. And if we look at the blue curve, not the blue shading region, but just the blue curve here, we notice that the derivative is above the x-axis throughout the interval from 1 to 5. So let's just remind ourselves what we know about the curve if I know a derivative is positive or above the x-axis on an interval from 1 to 5. We know that the antiderivative curve must be increasing over that same entire interval. All right, let's talk about these ideas and think about it. So let's consider the integral from -1 to 1 of radical 1 minus x squared dx. Again, this is just notation that we use here. This is the indefinite integral notation. The answer will be a number, and the number will represent the area underneath the curve of this curve, underneath the curve and the x-axis, between the curve and the x-axis, and it will represent the general, accumulated amount of change of the antiderivative curve on that interval. So right now we want to interpret two things. Interpret the integral as area and find its exact value, and then estimate the integral using Mathematica and compare your answers to the exact value. All right, so first, let's graph this curve. If I look at this curve, if we think about it, if I say y equals the square root of 1 minus x squared and squared both sides, I would get y squared equals 1 minus x squared, or I would get x squared plus y squared equals 1. Notice that was actually, this is just a semicircle. And using geometry, I can find the area between the curve and the x-axis because I know that this is a semicircle from -1 to 1. It's a semicircle with radius 1. So we know the expression of a graph of a semicircle of radius 1, area is equal to pi r squared, that's the area of a circle, but it's a semicircle, so it would be 1/2 pi r squared, which would give us pi over 2, which is about 1.57 or so. Now, that was the first part. The second part says estimate that same area using Mathematica. So what I'm going to do here is I'm going to stop for a sec, and I'll get Mathematica up on the screen, and we will take the integral from -1 to 1 of radical 1 minus x squared dx. All right, so here I have Mathematica up on the screen, and I opened up my Classroom Assistant palette here. And notice in the basic commands, we definitely have integrations here. You can see this is you can actually do a general antiderivative here using this button, but we're also going to use this one. So I'm going to try to make this a little bit bigger for us so that we can see it a little bit better. So we were going from -1 to 1, and our expression was the square root of 1 minus x squared. And our variable was dx. And notice Mathematica can do this work for us. Notice, there it is. It gives us the exact value that we just found. Now, we could get a numerical value of this to see what this is approximately equal to, right? There it is, 1.5708. So again, one nice thing about the calculation of these ideas of integration is Mathematica and other tools, our calculator can also do these calculations too, can easily help us to calculate what this area is. All right, so we used Mathematica to calculate this value, but we also could easily, notice we could easily do this one, just because it's a geometric object, we could find, using geometry, we can find the area between the curve and the x-axis. Now, what did we find? Remember, whatever function is sitting here is a derivative function of some other function. That function is called the antiderivative, and it will tell us the accumulated amount of change in the antiderivative over the given interval. Let me show you what I mean. Let's go back to Unit 2 for a second and think about what does the derivative tell us? Even in Unit 4, we also did this. Let's recall what we know about the derivative function and what it tells us about the antiderivative or the original function. If I said to you, here's a derivative function, and we're looking at this curve from A to B, what do I know about the antiderivative function, the function I can't see because I'm looking at this function's derivative? What do I know about the antiderivative function from 0 to 4? Well, if I'm looking at a derivative function, I know from 0 to 4, 0 and 4 are critical points of the f of x function because the derivative is equal to 0 there. Matter of fact, there's another critical point at 10. There's another critical point at 15. So I know from 0 to 4 on this particular interval, the derivative curve is lying below the x-axis, which means the derivative has negative outputs, which tells me that f of x must be decreasing on the interval from 0 to 4 because the derivative of f of x, f prime, is negative on this interval. This means the accumulated amount of change in the antiderivative function, f of x, which is the integral, must be negative. In other words, f must be going down on this interval from 0 to 4. That means when I look at a derivative curve and I think, okay, what does a derivative tell me? In this particular case, if the, quote, area, and remember in mathematics, area is almost always referred to as a positive quantity, but if we think, I'm going to put it in air quotes here, the area between the curve and the x-axis lies below the x-axis, the accumulated amount of change is negative because the derivative is negative on that interval, meaning that the original curve, f of x, must be decreasing over that interval. So the amount of change must be that the curve is going down. F of x must be going down. What do we know about the f of x curve from 4 to 10 if I am looking at the derivative curve? Well, from 4 to 10, which are also critical points, right? By the way, at 4, the derivative is negative, then 0, then positive, leading us, using the first derivative test, to know that x equals 4 is a local minimum. And from 0 to 4, the derivative lies above the x-axis, meaning that the f function must be increasing on this interval from 4 to 10, because the derivative is positive on this interval. This means the accumulated amount of change in that antiderivative, which is what the integral gives us, this number, this amount of change, must be a positive. In other words, f must be rising over this interval. How much does it rise? It rises whatever the area value is here, whatever I get as that number for the definite integral. So this definite integral tells us now one more piece of our puzzle. When I'm looking at a derivative curve, not only can I see the critical points of the f function at 0, 4, 10, and 15, I can also determine that the curve is f of x is going down from 0 to 4, And if I found what that area was between the curve and the x-axis, it tells me how much that curve, the f curve, the antiderivative curve, went down over this interval. And if I can determine the area underneath the curve from 4 to 10 and the x-axis, then I can determine the amount that the antiderivative curve f of x increased or went up over the interval from 4 to 10. So the number that we're finding for the definite integral tells us the amount of change in the antiderivative over a given interval. So again, recapping, what happens when the function is not positive? When f of x is below the x-axis? Then what we do is if f of x is positive for some values and negative for others in the interval from a to b, we take the sum of the areas that are above the x-axis and count them positively, think of them as positive numbers, and the quote areas that are below the x-axis and count them as negative values. So let me give you an example. If I said to you, here's a function, it is a derivative of another function. What do you know about the antiderivative function of this function from a to b? We know that the antiderivative function will rise from a to b because the derivative function that we're looking at is above the x-axis. How much will it rise? How much will the antiderivative function rise? Whatever this area amount is, that positive number, that's how much it will rise. So if f of x is positive on an interval from a to b, where f of x is a derivative function, because f of t, you can see it here, right? The integral from a to b of f of t dt is the area bounded of f from a to b and the x-axis, and it will be a positive value. If I'm given a function f of x where f of x lies below the x-axis from a to b, as in this case, then the definite integral is equal to a negative number. We will get a negative value. It will be the negative of whatever that area is from a to b. Now, what happens when some of the curve is above and some of the curve is below? Well, the integral from a to b in this case of this function f will be a positive quantity, and it will be whatever this upper area is. Let's call it area A. And the integral from b to c will be this area, area B, but that will be a negative number. If b is counted as an area and we think of it as positive, it will be the area above the x-axis minus the area below the x-axis will give us the integral from a to c. So whatever this quantity is minus whatever this quantity is would give us the area from a to c, or the accumulated amount of change in my antiderivative over the interval from a to c. So what is this doing? This is telling me that if this is a derivative curve that I'm looking at, if f is a derivative curve, it tells me that the antiderivative curve from a to b rises a units and then decreases or goes down b units from b to c. So from a to c, overall, the antiderivative will rise this much a units, fall b units. So overall, I will have what my integral is from a to c. Now in this particular case, it looks like a is greater than b. So it looks like overall my integral from a to c should be a positive quantity because the curve, the f curve will, the antiderivative curve will rise more than it falls. Now sometimes we ask, especially in physics class, we'll ask something like, well, how far did the curve actually move? Well, I moved up a units, but then down b units, But overall, I moved a plus b units where I'm taking the absolute value of the b